Hi everyone, welcome back to our channel. I hope you and your family members are doing good because that is the most important thing, and for rest we are here to talk. So we were following our pattern wise DSA sheet. The topic was binary tree and the pattern was serialization or construction. Today we will do the next question, which is construct binary tree from pre-order and in-order traversal. So let's read the problem statement. It says we will be given the pre-order and in order of a binary tree and we have to construct the binary tree, means we have to make the binary tree. Okay, and after construction we have to return the binary tree. So let's read the constraint. It says the pre-order length can be 3000. It means the number of nodes can go till 3000, right? Okay, and in order length and pre-order length will be same, obviously, because whether it is in order or pre-order, basically we are doing this on the tree only, right? So hence the length will be same. The values of pre-order or in order means the values of nodes can go from minus 3000 to 3000. It's also safe because integer can hold value up to 10 power 9, and if it is 3000 means we do not worry about the storage, means we do not worry about the long conversion. Okay, so here in this question we will be given the in order and pre-order traversal and we have to construct the tree basically. Okay, so we all know na ki first to create the whole tree, first we should get the root of the binary tree. So here is the root of the binary tree, but from the in order or pre-order, like we have to use these two order traversals to create the whole tree. So what do you think, where in the in order, so we cannot say where the root will be, because so how we write in order traversal? For in order traversal we should have stored left first, then the root value and then the right, means the root will be in middle somewhere. So we cannot check or justify ki what will be the root, but for sure from the pre-order we can find. Why? Because pre-order store the whole tree in the format of root first, then left and then right. So I don't know what will be the left child and right child from this much, but I am for sure about the root ki 3 will be my root. So if the root is 3 and in order how we have stored first left then root then right, then can I say ki if we will search this 3 in the in order traversal and we have found here, means for sure whatever comes before 3 index will be my left nodes of 3, means first I'll make 3. So I don't know where this 4 and 9 and how they will get arranged, but for sure 4 and 9 will come in the left subtree, and whatever is present after this 3 index, means 15, 20 and 7 will be a part of my right subtree. Can I say 15, 20 and 7? Yes. Yes. So it's very simple. Initially from the pre-order we have to get the very first node as root. Then we have to search for the index of this value here. Why we have to search for the values? Because it will be unique for sure, because if it won't be unique then for sure 3 would have come here also. Then we were looking for 3 somewhere here but we got at first position, then to the calculation will be wrong, right? So hence it's very important that all the values will be unique. And also in the constraint if you check here, it says pre-order and in-order consist of unique values. Okay, now next what we'll do, here we are done with the pre-order this. Now we will divide this much to go towards my left side and this much to go towards my right side. But what about the left parent in between 4 and 9? How we'll get to know that? Okay, so because this is pre-order traversal, then for sure after 3 whatever we have 9, right? So this will be my what? Left head or right head, means left side root or right side root, because we just saw na 4 and 9 were what? My left subtree part. So for sure whatever comes earlier, which is 9, so 9 will be the head of my left subtree. Okay, so after this we will consider again pre-order of this index. Okay, pre-order of this index 9, again we will search 9 position here. So before 9 whatever is there will be the left children's of 9, and after 9 will be the right children of 9. But do you think we should consider everything after 9, or we should have stopped after 9 and before 3? Correct. So it means in every call, like along with what we are sending in the root, so in a function, recursive function which we have to write, we have to clarify that this is your left and this is your right, and you have to search everything from this left to this right only. Because when we went for 3's left side, then we are allowed to move everywhere but only from 0th index to this index, means we cannot go towards this side, correct? So that's why we can say na ki before 9 was the left children of 9 and after 9 was the right children of 9. So after 9 what will happen? We'll move to the next index, which is 4. Okay. So 9 was 3's left side. Now we'll go to right side. So don't you think we should create the root first, then we should create the root dot left and root dot right, correct? So whatever we are able to understand, let's just write in the code format and then we'll collectively make the entire function. Okay. So first what we understood, key for sure root will be my, can I say in order, no, from pre-order, right? So we will have pre-order, but because we have to make the root, okay, and in pre-order though we have value only, okay. So before writing this, first we have to convert key, okay, root which we are assigning will be of type tree node, and tree node we know how the structure of tree node looks like. And now we have to create new tree node, and the value will be, value should be this 3, right? So from pre-order this should be my root, right? So pre-order, this means starting index, so we can say 0 as of now, but later on though we have to move on this 9, then for 4, correct? So let's initialize a index also and let's call it pre-order index. Okay, so let's initialize a index, pre-order index, okay, with 0 of type integer. So now we will read from pre-order, from pre-order the pre-order index, okay, and we have to do plus plus later on, so let's do plus plus here only. So what will happen now, from pre-order the 0th index value it will consider as root and the pre-order index will get moved ahead. So here will be my index, okay, here will be my index. Now this we have converted in the tree node, so this is like I have created my root. Now I have to create my left side and then later on I have to create right side. So for left side, because we are creating, okay, so whatever we will like, first so we have to call the same function. So let's say we have to make a build function, okay, and make a build function here. We will have build, we will have pre-order we have to send, okay, similarly we have to send in order. Now we have to send left and right index. I just showed you why we'll send the left and right index, so that when we are moving at 9 na, so ki 9's like wherever is 9, towards its left will come under left side and towards its right will come under right side. But it does not mean keep everything towards right, no, it should stop at here. So we have to send a left and right so that it will get to know ki, okay, till where I am allowed to move, okay. So now initially though obviously left and right will be 0 until last index, okay, because for the main root we are allowed to consider everything left and here right side, okay, but we have to send in the left. So what do you think, in the left will be as it is what was the parents left, but don't you think right will be this index minus 1. So first we have to find this index na, listen it very carefully, first we have to find this index. So to find this index we have two different methods. First is keep iterating in this and get the root value if it matches, like get the 3 if it matches, then assign it as your new index, correct? Okay, but if you do that now, first so for 3 you have moved to find this, then for 9 again you will move to find this, then again for 4 you will move to find this, then for 20 you will move to find for 20. So don't you think for every n number of nodes you are actually traversing n number of time to find it? And we know there is one data structure which help us to find the number index in just O of 1, and what's that? Hash map. Yes, so initially we'll move in the in order list and in the hash map we'll store every node with their index. So this is how we'll store. He will have 4 at index 0, 9 at index 1, 3 at index 2, 15 at index 3 and so on. Okay, now what will happen, we have to get the index for 3, right? So we'll go in the map and we'll just pick KH3, what's your index? So in just O of 1 time complexity we'll get the index 2. Okay, so we have to get that. So but before calling this build function we have to check the in order index. So we'll get int, as because it is a in order index, so let's say in order index. And how to get map, from map we have to get the map dot get what, root dot value, which is 3. Now in order index we'll have 3. Now what do you think, for left side the same call we have to call. In order pre-order will be as it is, left will be 0 only and right will be, don't you think we should stop till 9, right? So we have to send till here, which is in order index minus 1, correct? Similarly for right side we have to send from in order index plus 1 till last. Can I say that? So basically what I'm doing, I am actually allowing every function ki, okay, build your tree but only with this much node. Okay, build your tree only with this much node. Okay, so we'll write same pre-order in order. Okay, I'm assuming you'll write here, and then left will be same for left side, and for right we have to say in order index, okay, -1. Okay, and similarly we have to go for right side also, pre-order in order, left will be in order index +1 and right will be as it is. Okay, so we have sent this much for the left side. Now what will happen, this will go here, pre-order, post-order, and left will be this and right will be this. Okay, now again we will create the tree node like root but pre-order index. So pre-order index is here, right? So 9 will be my root, correct? Yes, 9 will be my root. Again we have to find the in order index from the map. So in order index will be 1 for this, correct? So now again for 9 we'll go for left side call and we'll send this 4, and for the right side we'll have nothing. So what we will have, can I say this in order index +1, which is 2, until 2. So don't you think, listen it very carefully, don't you think ki, like obviously this is a recursive call, so we should break this call at with some condition, right? So here the root cannot be null because this is not tree, this is list where we are playing with the indexes. So definitely to come outside the recursive call there should be some condition with the indexes only now. So we are assuming left will be always towards left side and right will always be towards right side. So don't you think when they crisscross each other means at like when they will be pointing just this node, suppose only 4. So it is possible to make node, right? Yes. But when they cross each other means left comes here and right comes here, goes here, then we can say ki no, it's not possible. Like there is no node in between. So hence a breaking condition will be ki if your left side is greater than right side, then return. Return nothing means null. Why return null? Because we are waiting for some type of node, correct? Yes. But as there is nothing to build, so return null. And because it is coming from left side and we are making a tree, so we have to save in root.left. Root.left. Similarly, we have to save this for root.right. So initially what happened? First we make 3. First we made 3 as a root. Okay. Now we went for left side and we went for right side. Okay. So now for left side also we picked 9. Okay. So 9 will be attached here. But before attaching, because it is a recursive call, so we'll go for the 9's left side, which is 4. Now 4's left side is nothing, so we'll return null. So to 4's left, it will be like 4 is a root and 4's left is null. Similarly, 4's right is null. As now we have to return something to their parent, which is 9. So what do you think? What should we return? Don't you think the 4, which is root itself? Yes. So after this, we have to write ki return root. So now what we made? 4 null null. So 4 null null, and in the previous call we had 9 as a root, correct? And 9 was waiting for left child. Left child was 4. So to 9's left side 4 will get connected. Similarly we will go for right side, we have nothing, so null. Again it will return 9 as root, that will get connected in 3's left. So this is how the tree will get created, like this. Now we'll go towards right side. For right side 20 is that node. Okay, because till that time in order index would have moved to 20. Now 20 is the root. Okay, so for 20 this will be left side, this will be right side, so we'll go for 15. Okay, similarly for 15 this root is null, left side right side is null. Now we'll return 15 and 15 will get returned and will get attached to 20's left. Similarly 7 will get attached to 20's right. Now we'll return 20, that will get attached to 3's right. I hope you understood. Okay, so the time complexity will be as we are moving to every node, each and every node. So obviously big O of n, where n is the number of node, which was 3000. And talking about the space complexity, in the recursive call we would have stored, like from every level we would have stored one node. So that's what level means, O of h, which is height, which is log n. Okay, so time complexity will be linear, space complexity will be O of h. Why the time complexity is linear? Because we have used hash map over there, right? But in total O of h, which is height of the binary tree, space complexity because of the recursive call. But because we have saved the indexes of in order tree in a hash map, that further takes O of n space complexity. As n is larger, so that's why space complexity will be n. Why n? Because we have reduced the time complexity over here. Okay, if we would have not used a hash map, then for sure the time complexity would have increased to n square, and that will be 3 into 10 power 3 multiplied by 3 into 10 power 3, which will be 9 into 10 power 6. Obviously, it won't give TLE because we know, if you have watched our time and space complexity video, that beyond 10 power 8, the code might give us TLE. But as it is 10 power 6, so it won't give TLE, but this is not optimized solution. Okay, so let's write the code in the editor. So here is the code what we have discussed. First we have to make the hash map, and then the preorder index initialize with 0. Now in the main function which will be given here, we have to run in the entire in order and save the indexes of every value in the map, so that getting the indexes will take lesser time. And now we have to call this build function. Now here we are just sending the preorder. Why? Because now we don't need in order list, because in order list was required to find the indexes. But as we have already saved in the map, so in order is not required. With map we can directly fetch. And the left and right index from 0 to till last. Now the breaking condition, if the left crosses the right, means there is no such element, not a single element. So it does not make sense. So it means we have to return null. Why? Because we are calling that build function recursively to fill the value at the roots left and right side, and that should also be a type of tree node. And as there is nothing, so that is the reason we are sending the null. Okay. Now after that, the first thing is we have to make the root. Where will be the root? Obviously with the preorder, in the preorder with the preorder index, which is 0. Now whatever we got, we have to fetch in the in order, and from that index, from left till that index minus 1 will be my left part, and from that index plus 1 till right will be my right part. And that's it. You know why we are returning root? So that it will get returned. Remember, the trees which we are making is not actually making up from the top, but we are making the node, we are going down, and then we are connecting back when we are returning this root over there. Okay. So that's it. Let's run the code. The time complexity is obviously O of n because we have used the hash map to store the indexes, and the space complexity will be O of n, of course. So this is your code in Java. I hope you understood. If yes, then here is the code in C++ if you are from C++ background, and here is the code in Python if you are from Python background. So that's it, guys. If you understood, and if you will submit on your own without actually copy pasting the solution, then only you are eligible to go in the sheet and mark the next question from this pattern as well. And that's it. I'll attach the sheet link and my social media links in the description. You can directly connect to me for any kind of guidance. And if you really like the way of teaching, please do hit the like button and subscribe the channel if not yet. You can even recommend this channel to your friends. Let's meet in another video with some more interesting questions, topics and patterns. And then keep learning. Take care of yourself and your family.